Thank you very much for the lovely introduction. Just going to check that this actually works. Okay, so my pointer. Okay, it doesn't matter. So yes, thank you all for turning up at 9 a.m. after what I'm sure was a lovely afternoon and evening on the beach and drinking many spritzes. So I appreciate the effort to actually make it in here this morning. For those of you that have not met me before, my name is James Gillanders and I am a postdoc based in the University of Oxford. And today I've been invited to present a summary or an overview, which I will try to do on spectral analysis of kilonovae, what we understand, where we're at, what's still unknown, and hopefully what we can try to do in the near future. So there are many interesting reasons why one should, I'll try and get rid of this, sorry. There we go. There are many reasons why one should be interested in kilonovae and neutron star mergers, but just to quickly set the stage for the reason that I think is the one that interests me most is the source of the heaviest elements in the universe. So this here, hopefully you're all have seen this before. This is a periodic table, and this one has been color-coded to indicate the production pathways for all of the stable elements in the universe. So you can see that there are a number of different production sites, okay, this does not work, doesn't matter. Pretend I'm pointing at this legend up here. There are a number of different production sites for all of the elements that we see here, but the ones I want to draw your attention to are the ones colored in orange. Okay, perfect. So all of the stuff down here, so these bottom 2 or 3 rows of the periodic table, these elements are produced either in part or wholly by the rapid neutron capture process, which is the most extreme nucleosynthetic process that we know of in the universe. So this is a very important process as it produces many of these very, very heavy elements that we are interested in for various reasons. Maybe you're wearing some gold and platinum jewelry, maybe you like making some bombs or something, or maybe you care about something like iodine, which is responsible for the development of life on Earth. So if one really cares about how these elements are produced and then how these things can be propagated throughout the local universe and then lead to the formation of the solar system and the Earth and stuff like this, you should really care about where these things are made and the timeline in which they are made. And that is why myself and many other people are interested in studying kilonovae, because they are the only confirmed site for the production of these elements. So the kilonova is just the name given to the thermal transient associated with a neutron star merger. And it is powered by the radioactive decay of many of these heavy, unstable R-process isotopes that have been synthesized immediately post-merger in the rapidly expanding ejecta. As I said, they're the only known source of R-process elements in the universe. There are other proposed sites, but this is the only one that has been observationally confirmed. And crucially, and will become important for finding these guys, which is incredibly tedious and difficult, they produce detectable gravitational wave and electromagnetic wave signals. And this is just a simple dummy cartoon that shows maybe potentially what one of these things looks like. So you can see 2 neutron stars here orbiting one another. As they orbit, they radiate energy away via gravitational waves, which causes them to inspiral. They eventually merge and eject a jet and then some material via various different mechanisms. And that is the material that is powering the kilonova. So many people have complained about their sample sizes in this conference so far this week. Some people were complaining they only had a few tens of objects. We have less than 10. So depending on exactly where you draw the line as to what defines a kilonova, you can probably get to on the order of 8 to 10 such objects. So here is just a nice summary from a paper by Gillian Ristinajad last year, where she went through all of the literature reported kilonovae and all of the swift short GRBs and compiled a data set that basically said there were probably 8 reasonably convincing kilonova, photometrically observed kilonovae from this sample. A few of these are quite interesting. I'm going to get on to 17017 and 230307A, but just to quickly say that 211211A is the first one that convincingly broke this split between short GRBs being linked to mergers in kilonovae and long GRBs being linked to collapsars, because this looks very much like a kilonova, but it is a long gamma ray burst. And then an interesting project that's ongoing, and I believe will be finished soon, is that Andrew Levan has done a similar follow-up work, and he has found that perhaps around 1/3 of all nearby GRBs are actually related to mergers, which I think would be a cool result. But photometry is no good to us if I'm presenting something on spectra, so I'm going to summarize the even smaller data set that we have of spectroscopically observed kilonovae. This comprises 2 objects, which is not good if one wants to do a sample study, but you do your best. So the first of these, I'm sure everyone has heard of before if you work in the transient community. This is 17GFO or GRB 170817A, GW, blah, 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 blah. This guy was discovered via both a gravitational wave and a short gamma ray burst signal. It was quite well localized. Its optical counterpart was identified only 11 hours post GW trigger, and it was associated with a galaxy very nearby, 40 megaparsecs. Because it was discovered early, because it was quite local, it was very it appeared quite bright for quite a long time, so it was possible to get good observations, high cadence observations for many days. The second such event is AT 2023 VFI and GRB 230307A. So this one was again discovered through a gamma ray burst, no GW signals, it was too far away and the GW detectors were offline. Its counterpart took a little bit longer to find, but it was eventually associated with a galaxy at a distance of around 300 megaparsecs. And really cool, this one occurred after the launch of the James Webb Space Telescope, so it was possible to get really nice, deep infrared imaging and spectroscopy of this guy. So here's just a pretty picture from a composite of the James Webb imaging. Okay, so when one thinks about the spectra of these objects, there are very, very, very many spectra taken of 17 GFO. It was the first convincing kilonova. It was very nearby. Everybody wanted to go at our slice of the pie. So everybody with an instrument pointed at it, but the spectral sequence sort of has like a gold standard or whatever, and that really comprises the 10 X-shooter spectra that span from the UV through to the infrared and cover a nightly cadence from 1.5 to 10.5 days. Supplemental to that, you have some intermediate and late phase HST spectra, and then you also have some very, very early featureless blue optical spectra that were acquired immediately after the counterpart was identified. So this is sort of when people talk about, looking at the spectra of the kilonova, this is almost certainly what they mean. This is basically this is the subset of the base spectra that we have of this object, and this is what we're trying to model and reproduce and understand. I don't want to give a super biased summary of the work I have done because this is something I've been working quite a lot on for the last 7 or 8 years. So I'm going to try and cover a flavor of what other people in the community have done as well. But if I've missed a favorite project of yours, I apologize. You can let me know and I'll add it to the next time I give this talk. So various people tried to do this and tried to interpret the spectra of this object as it happened. So here's just one example. So Stephen Smart had a paper in 2017 right after where he tried to do some very simple TARDIS radiative transfer modeling to explain the absorption feature that appears at around 8,000 angstroms in the early spectra. They produced a model that somewhat matches the data, and their plausible identification at the time was cesium and tellurium. This didn't really hold up. 2 years later, Dara Watson came along and said, no, that's probably not right for various reasons. We think it is strontium. And he, again, here did some simple TARDIS radiative transfer modeling, but instead of having an arbitrary composition profile, he invoked the solar or process composition profile and found that actually you can get a very prominent absorption feature that matches here from strontium. So he said, great, this is strontium. There's a bit of reticence to accept this at the time because only 30% of the strontium in the universe is produced via the R process. So you don't expect much of it to be produced in kilonovae, for example. But it turns out you need a very, very, very small amount of this material to produce a strong absorption line or lines. So people sort of looking at it in a bit more detail and studying it a bit more decided, yeah, this is probably convincing. Here's an example. I'll probably talk about this in a few more slides in a bit more detail, but this is an example of something I did with TARDIS a few years later, showing that, yes, the strontium thing works. Similar project from Nana Demoto. This is a very nice project. They use the Tanaka radiative transfer code and generate a bunch of models to try and identify multiple different features in the spectra. And here they're claiming that you can see yttrium and zirconium in the data, and then also lanthanum-3 and cerium-3. So this is the first proposed identification of lanthanides in the spectra. Then you have Kenta Hodokozaka in 2023 pivoting to not look at the early spectra, but to look at the late spectra. And here he has produced some models to reproduce the latest 4 X-shooter spectra of 17 GFO. Specifically, he claims that this big booming emission bump at 2.1 microns or 2 microns is due to tellurium-3 transition. And then even more recently, you have Salma Ramouni also running some more radiative transfer models using the Tanaka radiative transfer code and claiming that in addition to lanthanum in this feature, you also get a contribution from gadolinium-3. So there are further people trying to converge more and more to identifying more and more spectral features and also looking at a bit more detail at the ones that are less obvious and less prominent. So immediately, the first big one was the one at 8,000 angstroms. That's the one everybody wanted to do. Now that that's been claimed, everybody's trying to do the smaller absorption lines and the ones that are less obvious. So it's a fun game to play. But that's sort of where we're at. Just to give a bit more detail on how this type of thing generally works. This is just an example because it's the one I know, because it's the one I did. But you can pretend that all people that do this type of thing sort of do roughly the same thing. So here we take the TARDIS radiative transfer code. It can be any tool you want. It doesn't matter. This is the one we used. For this one, instead of using an arbitrary composition or the solar composition, we fold in realistic composition profiles derived from a hydrodynamical merger of neutron stars, of a binary neutron star system. And then we also, at the time, included all of the calibrated, publicly available atomic data for these very heavy elements. So this data set, in principle, should be the best thing that was available at the time to do this type of study. However, it turns out that actually, in practice, the data is very, very incomplete. So we did the project anyway and have a caveat about the results. But the point here is that we can reproduce the early spectra very well with this tool, similar to the previous projects. But crucially, we show that you need a composition at very early times that only contains things like strontium, yttrium, zirconium. And then at later times, you need to also include quite a substantial amount of lanthanide material to suppress the flux in the blue and reproduce the SED of the observations. Good result, held up for a few years. Then Andreas Fleurs came along and annoyingly did a really fantastic job of reproducing a new calibrated, complete atomic data set for the lanthanide species. So when he did this, he said it to me and said, how about you give this a go? How about you try and model the spectra again using this new data set? So we did. We get a very similar quality of fit for the spectra, and we find that it's the same sort of elements contributing, but crucially, because we now have a much more complete data set with many more lines than what we included in 2022, the effective opacity for the same amount of lanthanide material has skyrocketed. So we can reproduce a similar quality of fit, but we now have to drop our lanthanide mass fraction from 5% to 0.25%. So this does roughly agree with other claims in the literature for the lanthanide mass fraction in the ejecta, so this is probably okay. But it's just an interesting demonstration of the fact that, you know, even in 3 or 4 years, the analysis can completely change because we're so sensitive to very many uncertainties in the atomic physics and also the nuclear physics, which I'm not going to discuss, but we can discuss that later if people are interested in it. And this is just to show all of the lines that are in the new atomic data set versus what we had here. So there's a factor of very many here increase. Okay, so that's kind of all I want to say about 17 GFO, but we can come back to it after if people are interested. But the one that I really want to talk about now is 2023 VFI. This one is super exciting because it is newer, it is shinier, and also we have some nice James Webb Space Telescope data for it. So this is again the image from the color image made from the different photometry images at the time, and then these are the two spectra that were acquired at 30 and 60 days. So you can see here that there is, interestingly, a big booming emission feature in both the 30-day and 60-day spectrum, which also agrees with the position of the feature that was in the late phase 17 GFO spectra. You can see here that one is overlaid in orange. So that's really interesting. We should take a look at that. So that's what we did. So similar to the previous thing, I'm just going to show my example because I'm trying to promote my work, I guess. But here we did a project where we looked at the spectra and we tried to basically reproduce them with a very simple empirical model in order to quantify the contribution of the continuum. And then when we understand that, then we can make some claim as to where there are emission features in the spectra and then possibly try and do some line identification for those. So we do that, we get pretty good fits to the data, and we find that there are 3 emission lines, 2 centered around 2.1 micron, and then another one plausibly over here at 4.5 microns. When one does a line identification search for these, you uncover a very large line list that encompasses many of the most abundant species across all 3 R process peaks, but there are reasons to favor and disfavor based on nucleosynthetic arguments. I'm not going to go over the details here, but we can also discuss after. But the key point here is that specifically for the feature at 2 microns, that does work. One gets a reasonable short list of 7 or 8 ions, but the one that is most interesting, I think, is again this tellurium-3 forbidden transition here that was initially identified by Kenta Hotakazaka in 17 GFO. So this is marked by this big blue vertical line here, and you can see that it is smack bang in the middle of this feature in 17 GFO, and it also lies between these 2 emission lines in VFI, and then also agrees with this position, or roughly with the position of the feature at 60 days as well. So I think this is really cool. But as you can see, there are many candidates for this one feature. The best way to do a convincing line identification search is to identify multiple transitions belonging to the same ion or the same element, and then you can really more convincingly tether your IDs to the data. So that's what we took a look at here. We basically said if you take the observational data at 30 and 60 days and you subtract off the continuum, what are you left with? And you're left with these, again, your big features at 2.1 micron, and then you're left with some scatter around the continuum here, or around 0. So then we say, okay, we understand the atomic physics of tellurium-3 very well. If all of the emission here is produced by this transition at 2.1 microns, we can make a very accurate statement or a very precise statement as to how bright the next strongest transition should be, which, if this is tellurium-3, should be emitting in multiple transitions. So we do that, and we figure out that you should get these 2 piddly wee things over here at 2.9 microns. So this is the next strongest transition for tellurium. It doesn't really rise above the noise in the data, so we can't convincingly rule out tellurium or rule tellurium in. It's more just, I guess we should go again next time and try and get better signal to noise data or something. But if the temperature of the system is slightly different, or if the density is slightly different, or if we get better signal to noise data, then potentially we can do this and identify these features, which will be really cool, or we can rule tellurium out and say, no, it must be something else. So that's sort of the state of play here for this particular feature in this particular kilonova. But again, possibly next time with better data or a slightly different system, we might be able to do this more convincingly. So this is an interesting slide. I don't expect you to look at it all. And again, so this is a summary of all. This is my attempt to summarize many of the proposed line identifications in both kilonovae to date. If I have missed your favorite work, I do apologize. Please let me know. I will add it to the list. I've tried to be somewhat unbiased and somewhat comprehensive here, but it's possible there are many papers on this topic. It's possible I've missed something. Point here is not to read all the references and to look at all the things in detail. It's just to show that actually there is many people doing tremendous work on this topic, trying to identify different elements in the data for both objects and trying to use that to then make some statement about the production of our process elements generally. So you can see here that many of the things colored in orange have been targeted here. So I mentioned lanthanum, cerium, and gadolinium. These are pretty cool and somewhat convincing identifications. You have stuff like tungsten, so around the third peak. If there is one that is marked like this does not mean that platinum and gold was not produced. This means that somebody looked for it and did not find it. So similarly for tin, there is no strong evidence for tin in the data. That does not mean tin was not produced. But the really cool thing, just to quickly draw your eye to, is that not all of the things that have been studied and identified are actually colored in orange here. There are elements like rubidium and selenium that have been claimed in the data that were not expected to be produced in substantial quantities in these types of systems initially. It is now clear that actually you can get down to elements a bit lighter than what was previously proposed, and now you can possibly identify things like this. And then also, those with an eye at the top corner will have noticed that helium has also been marked here. There's a really interesting ongoing debate as to whether the data, the absorption and emission at around 1 micron in 17 GFO could actually be contributed to by the helium 10830 line, either in part or completely at early or at late times. This is an ongoing thing that people are working on, and it is the current status is that it is probably some sort of mix of the two, with one becoming more important than the other at different phases. But this is a really cool thing to watch out for. And yeah, that's probably all I want to say there. Then to think about, so we've sort of looked at the two objects that we have. We've looked at where we're at with the line IDs and the modeling of the data. Then to look sort of near future, what do we want to try and do? I think we want to try and identify more new elements and try and constrain more identifications to try and do that kind of thing. So we should continue what we're doing, but with more data and better data. So thinking, you know, these things are incredibly rare. We need to make sure we optimize our observations for the next object. Probably in practice, that means that when we get one, everybody will just point everything at it. That's fine. But one should, in principle, think at least about what you want to do. So this is a slide that I've stolen from Anders Björkstrand, that I think makes this point quite nicely. So this is a radiative transfer model for a kilonova at 10 days. It doesn't matter, the details don't matter. The key thing that I want to get across here is that if one is curious about probing the bulk composition of the ejecta of kilonovae, one needs to make sure that you're actually probing the bulk composition or the regions of the bulk of the composition. So here is a model that has been color-coded with all of the different colors corresponding to different velocity bins of the ejecta. So the velocity bins are marked here, so 0.25 to 3C all the way down to 0.05 to 0.1C. But the number in brackets here is the total amount of mass of the system that is enclosed in those velocity bins. So modeling the early phase spectra gets you down to around 0.2 or 0.15C. That's great, but you only probe, you know, something like 20% of the total ejecta. If you really care about figuring out what the bulk of the composition is, you want to get down to this low velocity regime. And if you look down here, all of the emission from this purple zone comes out in the infrared. So you can probe a small amount of this from the ground with X-shooter, but above 2-3 micron, you really need to hit this guy from space. So the key point here is that the James Webb Space Telescope is vital for this type of science. We got it for the last object, but we want to get better, higher cadence, higher quality data for the next object. So we really need to focus in on this, I think, a bit. Just to sort of make that point again, but applying it now to data. So this is a similar model, again, from Anders' group. Quentin's also heavily involved in this type of study. So here they've used an NLT radiative transfer code called SUMO to generate a bunch of models for some light or process dominated kilonovae and said, screw it, we'll compare it to the data. It's not expected to match, but let's see how it does. So the key point here that I just to quickly highlight is that these models all produce a booming emission line at 2.1 microns, which is really cool, in agreement with the data approximately. But the key point to highlight is that in all of these cases, at all of these phases, it's a blend. So tellurium-3 does contribute to the feature at all times, but it is subdominant to things like krypton or selenium in these models. Probably that's reasonable. There's expected to be very many lines overlapping and blending in these systems. Single line identification is very tricky to convincingly claim, but something like this is quite interesting, and this is really probably where the near future and mid-future is going. People doing more complex analyses and really doing better work than the simple, here is a line that matches and it's that element or something. And then just to quickly comment, they're not really expected to match, but you'll notice that none of these models have a strong continuum, so they don't match this rising red continuum here in 23 VFI. They don't really match this red continuum here in 17 GFO either. And super. That's a bit of an ongoing debate for the last few years as to what could be causing this, but there's a really interesting result from Nana Demoto and Kenta Hodakazaka's group. This only hit the archive last week. I have not read it in detail, but this is a really cool work that's been presented a few times at conferences before and has caught many people's eyes. Basically, they've been arguing in this paper, or they are arguing in this paper, that this rising red continuum in 23 VFI and possibly also in the later stage spectrum of 17 GFO is plausibly produced by our process dust. So I don't understand the full details of this, but basically if you have a rapidly expanding medium that cools, you can actually form heavy element dust, which can then thermalize and produce some sort of cool thermal continuum. So you can see here, this isn't really expected to match the data perfectly, but you can see this model with dust actually does get approximately this continuum here, which is really cool. So that's something to keep an eye on. If this holds up, then that's really, really interesting and potentially provides another way to find or to identify heavy elements, because you would then get dust lines as well as elemental lines. And then finally, to talk about the observational outlook for future kilonovae, the rates is really a big problem here, but if we want to make sure we know what we're doing for the next object and optimize what we're doing, really I think the key point is observation sampling the infrared for the bulk composition argument I made earlier, and really getting to late times. The later you go, the more diffuse the material is, the deeper you can probe because the optical depth is lower. So really you're thinking along the lines of you want to hit in the infrared, you want to hit late times, 30 plus days. So we should be really trying to come up with a strategy to do that. James Webb is perfect for this science, and we're actually very lucky. Previous people have complained about not getting time and to observe their objects. We're the other way around. We're very fortunate to have gotten time, but we're not getting any objects. So hopefully one goes off in the next year or so and we can get some decent data for it. And this is just some model prediction for what we think the next object will look like. So if you were to observe it in the near infrared and then the mid infrared, we think you will get something that maybe potentially looks like this with all of these broad emission lines that we can then use to constrain the composition again in the next object. And I guess I spoke a little fast because I'm a minute or two under, but that's fine. We have more time for questions. Just to quickly summarize, kilonova spectra they provide non-paralleled opportunity to study the production of our process elements and to constrain their abundances through the local universe. There have been actually, this should probably be many, not some, but there have been many species IDs proposed, but none of them are confirmed. You really do need to get into more quantitative types of modeling, and you really need to have multiple line identifications for the same element to really convincingly claim a specific ion, but we're getting there. Further work is needed, better modeling, improved atomic data, improved microphysics, improved nuclear physics. There is a long list, but we're getting there. There are a lot of people working on this problem, and they're very, very good, so I'm sure we will do some nice work in the near future. And then just to say, James Webb is vital for this type of work in the future, but crucially, the big thing we're missing is we need more kilonovae. So thank you very much. Happy to take some questions.
Yeah, thank you very much. Okay, so
great talk, James. Thank you. So I have a question. I'm a bit intrigued by this new work, like where you see that the lantern diffraction goes down, like to this point, 25% or so.
Yeah.
So I guess here, so you're obviously like you're probing the line forming region, right? So I was wondering, like, do you have a sense of how this number would change if you go? I mean, because you're not probing the deeper part of the object, I guess, in the spectral time series you're doing. And the follow-up question is whether, I mean, whether you can do a similar analysis also on the James Webb for 230307A, or that's just one spectrum and you really need a spectral time, because that's at later phases. So.
So Very good question. Good caveat that I probably was supposed to say and I forgot to. Here, when you do the early phase analysis, you're only probing the outer line forming region. So here, when I make this statement that 1/4% of the mass fraction is lanthanides, that's only in the region above something like 0.1 or 0.15 C for 3.5 days. It's very, very difficult with this type of work to probe deeper and to constrain this number throughout the entire ejecta. This is almost certainly expected to rise. If there is a substantial amount of lanthanides produced, they will remain probably below this 0.1 C, 0.15 C boundary that is invoked here in this analysis. To get a better number, and I believe Christine is the talk after me, she might have a number, or maybe she didn't include it, but when you do something like more quantitative with Sumo or with Artis or something like this, you can get a number that is you can do an analysis that is sensitive to the entire ejecta, which then allows you to get a better number. So this number we think is good and is reliable, but only for that, you're right, for that outer region. And then for the likes of 23 VFI, in principle, yes, one can get a number. You cannot get it from something like this, but again, you can get it from the more quantitative analyses. So the work from the Sumo models that I showed, for example, in principle, you could do one of those, and I think Quentin has done this, with some lanthanide material, and you can make some statement to approximately how much of these elements are present.
Very nice talk, James. So as you know, with GWTC5, the rates of binary neutron stars is plummeting. So it's getting harder and harder to explain the local R process yield with compact binary mergers. So given this very nice sort of element by element description of heavy elements, the question I have for you is, what are your thoughts on heavy element production or R process production in non-merger scenarios? And ongoing searches for that.
Yeah. So there are a few different scenarios. One that has recently come out that looks quite promising is giant magnetar flares. So here you have an outburst from the surface of a neutron star, and a very small amount of material can undergo R process nucleosynthesis, or so it is proposed. And from that, you can potentially produce quite rapidly after the formation of the neutron star quite a few heavy elements. The estimate for the rates of these and the amount of material ejected per event means that you can probably get to around 10% or maybe 15% of the R process material in the local universe via this mechanism. This is very difficult to do observationally. These things are very short-lived. There is a proposed identification of one of these such systems in the last 20 years, but given the data, it's very unclear as to whether this is real or not. I think further work is needed there. Similarly, there are proposed models where you have heavy elements produced in something like a collapsar, where you have maybe you synthesize R process material as well as the typical iron group and intermediate mass elements. In that case, disentangling the signature from R process elements from the rest of the supernova signal is incredibly tedious and incredibly difficult. Many people have worked on this. I tried to do this at the start of my PhD. This is a very non-trivial problem. Probably to observe the R process signal, you need to go to incredibly late times. You need to go to the infrared. You need to get out to somewhere where the line density is low enough that you can conclusively identify a line as being R process element and not something from the typical supernova or something. And then there are other systems like a kilonova in a supernova or a super kilonova or something that I guess we'll be talking about later, and we can discuss that. But observationally from the spectra, it's very difficult to disentangle R process production from the supernova production if you have these two systems doing the same thing, or doing both nucleosynthesis pathways in the same system, I should say.
Thanks for the nice talk. You mentioned that 35 of GRB at redshift lower than 0.3 are likely to be associated with merger. What is the reasoning behind that allows you to get this number?
So basically the argument here is that within a redshift of 0.3, you can, for all of the objects that have had an identified counterpart, you can get a redshift from the host galaxy, or not identified. If you have a nearby object, you can identify the host galaxy. If you identify the host galaxy, you can get the distance, and then from that you can say if this is a typical GRB supernova, it should be this bright, and you can, with follow-up observations, rule out the presence of that supernova to very, very deep limits. So the idea is that if it's not a GRB supernova, it could be, or it is plausibly a GRB kilonova. So in many cases, The distance is known, but there is no optical counterpart to the GRB. And in that case, then you can say, well, it's something that has to be 100 times fainter than a supernova. It's not obvious what that could be beyond being something like a kilonova. So this is an upper bound because it is possible that there are other things that in play here, right? You could have, for some reason, an incredible amount of dust, which is extinguishing your signal, and then you do not detect it. But the upper bound here is that actually around a third of these do not have an optical counterpart, down to very strict limits. And then with that statement, you can then say that they could be kilonovae.
Okay, thank you.
Thank you. Thank you. Okay, let's see setup. Next speaker is
Yes, thank you. A lot of what I want to talk about has already briefly been touched on by James, so a lot of this could seem a bit familiar, including my introduction slide here, where these again are the spectra of the kilonova AT 2017 GFO, and the lines marked on here are indicating where the strongest spectral features are in this series of spectra. And as James has already talked about, the first identified feature was this strontium-2 triplet, and then there's this question he touched on of whether under non-LTE conditions it could potentially be helium-1. That is still an ongoing discussion and not something I'm going to really get into in this talk, but still interesting. We also have this lanthanum-3 feature that was then identified, and then more recently it's been suggested that there's gadolinium-3 also contributing to this feature. And cerium-3 here. I don't think he mentioned that this could potentially be yttrium-2. It could also just be the blue wing of the strontium-2 absorption feature, but there is a suggestion yttrium-2 could be at these wavelengths, and also this forbidden tellurium-3 feature. But pretty much the point James was making in his talk was that a lot of these features still aren't quite certain. To really confirm these features, we still need more detailed modeling. And a lot of these features were identified by a backwards modeling approach, where it was identified what the strongest lines were, and then comparing to the spectra, okay, there's a feature in these regions where there's a strong line. It could be this feature. But what I focus on is a forwards modeling approach, where we really start with a composition that's come from a merger simulation, and then we go through with the radiative transfer and calculate the spectra that come from that. So this is what I mean by this forward modeling approach. We start with this neutron star merger simulation that comes from my collaborators, and they also provide nuclear network calculations for these. And then they go into my radiative transfer calculations. I use the Monte Carlo time-dependent radiative transfer code ARTIS, and the wee animation that was there just shows packets of Monte Carlo photons propagating through expanding ejecta. And whenever they escape, we can bin up all these photons and get time-dependent, direction-dependent light curves and spectra. I also need atomic data at this stage, which is very important for kilonova modeling. For these lanthanides, we have millions of these transitions that we need to model. I use a line-by-line approach where we really calculate every line transition from all of these lanthanide species. And then I can get time-dependent spectra. The first thing I kind of want to talk about are that 3D simulations really seem to be important for kilonova modeling. The main reason for that seems to be that kilonova ejecta are highly asymmetric. What I'm showing here is a 3D rendering of the density structure that comes out of a neutron star merger simulation. And on the right, I'm showing the light curves that come from this 3D model. The colored lines are the light curves in different directions. The black line shows the 1D version of this model. And you can see that the 1D model does not look like any direction in the 3D model. So this isn't just a detail, it really is necessary for accurately modeling kilonovae. It has recently been inferred that the kilonova in 2017 was highly spherical, which seems to contradict this highly asymmetric ejecta that we get from these merger simulations. They inferred that it was spherical by fitting this P Cygni profile to the strontium-2 feature observed in AT 2017 GFO. And they find that the shape of this feature was most consistent with a spherical photosphere, not prolate, not oblate, perfectly spherical. So they used this to suggest that the kilonova was spherical. I've applied the same analysis to a spectrum that came from the asymmetric model on the previous slide. And I find that from one pole, we do get a best match with a spherical photosphere, but from the opposite pole, we get a better match from a prolate photosphere. So this shows that an asymmetric simulation can be consistent with these spherical constraints, but once we finally get more observations, not all of them should appear spherical. Another thing that we really need for accurate kilonova modeling is accurate atomic data, which again, James already touched on. So we showed that accurate atomic data really is critical for this kilonova modeling. We compared an uncalibrated, theoretically calculated atomic data set, which had uncertainties in the energy levels, which led to uncertainties in the wavelengths of the transitions. That's the top plot here on the right. We compared it to when we replaced only strontium, yttrium, and zirconium with experimentally calibrated atomic data. And you can see that the spectrum completely changes. So in the uncalibrated atomic data set, this is where the strontium-2 feature formed. But in the calibrated atomic data set, this is where it formed at the correct wavelengths. So experimental data is accurate, but it's still incomplete, making the theoretical data necessary. But theoretical atomic data, while it's complete, it's not sufficiently accurate. So when we use this calibrated data set, we do get pretty good agreement with the evolution of the kilonova. We get pretty good match with the spectra. One caveat is that this model, the mass is about 10 times lower than was inferred for AT 2017 GFO. And that's because in this model, it's only the dynamical ejecta included. This is just a limitation of the hydrodynamical modeling. It's very difficult to follow in 3D particularly, the evolution out to later times. But despite this, we do get good agreement with the observations, except at these redder wavelengths beyond 1.2 micron. You can see in the kilonova spectra, the observations, there are features out at these wavelengths, whereas ours is very flat. We don't get any of these features. But now we have Andreas Fleur's calibrated atomic data for the lanthanides. And when we include these, we do start getting these features out at these redder wavelengths. And these seem to be in good agreement with the observations. So now I want to talk about a recent study I've done where I've explored the diversity of kilonovae. I have 18 new merger models with different neutron star masses and different equations of state. Again, these only include dynamical ejecta, so the masses are too low. But we get a range in ejecta masses and different density and abundance structures. So we get a sample that we can explore a bit how the spectra change with these different compositions. These are all of the spectra that come out of these models in the polar direction, now compared to 17 GFO. If I compare them at the time where the SED, the color, is the closest to observed for 17 GFO, I find that it shows very good agreement with the observed spectral sequence of the kilonova. It shows similar spectral features and shows a good similar overall evolution. Zooming in on one of them and scaling the spectra, it shows that this really does show very good agreement with the observations. We get the strontium-2 triplet absorption, we get lanthanum-3 with blended gadolinium-3, cerium-3, all of the features that have previously been suggested in the literature. But this is the first time it's been shown self-consistently with this forward modeling approach. We didn't tune any parameters here. This is just what came out of the hydro model and the rate of transfer and comparing it to the observations. So this is the same thing, but for all of the models now. And one thing you'll notice is that all 18 of these models all show the same strong spectral features, despite the different ejecta masses, the different densities, the compositions. They're all very similar. So they also show this strontium-2 triplet, and the lanthanum-3, gadolinium-3, and all of these cerium-3 features. And they all seem to be in pretty good agreement with 17 GFO, although they're often a lot more blue shifted than were observed. So this gives a bit of a prediction. We can expect a difference in the strengths and velocities of the features in future kilonovae, but it seems that in the polar direction, these will be the strong lines that will appear in all of the polar direction spectra. So you may have noticed that 2 of these models show a feature that I haven't spoken about yet. This is circled here. This is yttrium-2. And yttrium-2 was suggested to be in the spectra at these wavelengths. So this shows that yttrium-2 can indeed affect this region of the spectrum. Thank you. But in these 2 models, they don't show particularly good agreement with the observed spectra. But interestingly, these 2 models that show the yttrium-2 feature have the lowest lanthanide fractions in this polar direction. So I think these are the numbers that James was mentioning. These kind of numbers from these 2 models that show yttrium-2 are in agreement with James's number. But the rest of the models, which apart from that yttrium-2 feature, show pretty good agreement with 17 GFO. They can be up to around this lanthanide fraction. So interestingly, the presence of an yttrium-2 feature could provide an additional constraint on the lanthanide fraction and constrain it to lower lanthanide fractions in the polar direction. So with that, this is my summary. Asymmetric ejecta can be consistent with the inferred sphericity of 17 GFO. Accurate atomic data is crucial for kilonova modeling. We get predictions of strontium-2, lanthanum-3, gadolinium-3, and cerium-3 for all of the models. The exact strength of the features vary. There will be some diversity, but they have the same features in common. And future kilonovae are likely to show similar spectral features to those in 17 GFO in the polar directions based on these simulations, which only included dynamical ejecta. So in future, we do need to investigate this further, including the later ejecta components. Thank you.
Thanks a lot. I found it really very, very nice talk with a lot of information, and for me that I'm not in the field. A question on the fact, sorry if I missed it, the fraction of electrons or neutrons that are in the model, so you take it from the observation, you try different fraction and you see what they are?
No, sorry, I should have explained this better. So these are the lanthanide fractions in the neutron star merger hydrodynamical simulations in the polar direction. So if I look to different directions, the equator, the lanthanide fraction is a bit different to this, but this is the region of the ejecta that's contributing most to these spectra in the polar directions, and this is the lanthanide fraction in that direction.
Okay, so in your theoretical framework, all the kilonova will look the same in a sense? In this distribution of lanthanide fractions?
So the equatorial spectra do look different to the polar direction. Yeah. These models suggest that, yeah, if we observe another kilonova in the same direction, I'm not saying the strength of the spectral features will be the same and the velocities may be different, but I think it will still be these strong lines that appear.
Okay, just a few questions on what's the situation in the atomic data. So I saw here these floors of work bringing new data, but are there groups enough? I mean, there are enough group working on this to improve this. What do you see as perspective on this topic?
Yeah, so it is obviously still very much ongoing work. This new data set from Andreas is great. We now have accurate enough data for all of the lanthanides. Still missing seems to be the actinides. We don't really have data for them yet, so potentially more could appear from that. It's still not quite complete for lighter elements, but it seems that the lanthanides tend to dominate a lot of the opacity. So I'm not sure how much the lighter elements would win at this stage if we had better data for them. One big limitation at the moment is the data to go to non-LTE. So these are all LTE calculations. So I have the energy levels and the transition strengths, but we'll also, to go to non-LTE, need all of the cross sections for photoionization, for recombination, and these are all still very, very incomplete. And there are a lot of groups working on it, but we need all of the lanthanides, and that is a big, big task for atomic physicists.
Yeah, thanks, Christine. Very nice talk. So I was wondering about this plot here. So you showed well, I'm looking at the strontium feature, for instance, but you obviously, I mean, you mentioned that you are only considering dynamical ejecta. I was wondering if you've done some simple exercise, like if you add some extra flux, that would be coming from post-merger wind ejecta, whether I would assume these features will be kind of wash out if they only come from dynamical ejecta. Have you done an exercise? I mean, what I'm wondering is whether you need also some strontium from the post-merger wind, or?
So I did do something like this in 2023 whenever I was doing gray calculations. So I'm not really sure for the spectra, but definitely whenever I added this extra mass at the center in the gray calculations, the brightness did come up to about where 17 GFO is. My thoughts on whether the spectral features will change with this inner late time ejecta is that I think at these early times, it's mostly dominated by this fast ejecta on top. And I don't think the spectral features will change too much because we already have this outer ejecta, and then the later time should be inner, but it needs confirmed with the simulations.
Okay, next speaker, Michela Maria Dinatolo.
Okay. Hello, everyone. I'm Michela Dinatolo, and I'm a first-year PhD student in Milan. And I will talk about my latest work, which is multi-wavelength properties of short gamma reverse with extended emission observed by Swift. So first, I will give you a brief overview of what are gamma reverse. They are intense flashes of gamma ray radiation, and they are extragalactic sources. And their emission can be divided into two phases: the prompt emission, which can last from milliseconds to tens of seconds, and is the phase during which the gamma ray burst releases most of its energy, mostly in the gamma ray band. And then it is followed by the afterglow emission, which can last from days to weeks, and it can be observed from the radio band to the TeV energies. Based on the duration of the prompt phase, we can divide the gamma ray burst into two phases, into two classes: short gamma ray burst, which last less than 2 seconds, and long gamma ray burst. This phenomenological classification is also related to some intrinsic properties. For example, for the prompt emission, we have that short gamma ray bursts show harder spectra than the long ones. They have null spectral lag. And for the afterglow emission, we have the short gamma ray bursts are less luminous than the long ones. They occur in all type of galaxies with a low star formation rate and a high offset. Also, short gamma ray bursts are associated with the kilonova emission, and the long ones with a supernova emission. These reflects also differences in the progenitors, because long gamma-ray bursts are produced by massive star collapse and the short ones by compact binary merger. But this classification is not a strict divide, because we observe some events, some short gamma-ray bursts associated with a kilonova emission, with a supernova, emission, and long gamma-ray bursts with a kilonova emission. There are some gamma-ray bursts which challenge this historical classification. For example, we have gamma-ray bursts with extended emission that are characterized by an initial pulse followed by an extended emission, which is softer. In a lot of cases, we have the association of these gamma-ray bursts with a kilonova, it's very strange because they should be classified as long gamma-ray bursts, or we cannot find a supernova emission. So the main question is, do short gamma-ray bursts with extended emission share the same progenitors as standard short gamma-ray bursts, despite their long duration? So we studied a sample of short gamma-ray burst, which is the SVOM sample, which is a flux-limited sample with the highest completeness in redshift and with controlled selection biases with favorable observing condition for the determination of redshift on ground. And we compare them to the long of the BAT6 sample, which is the analogous for the long gamma-ray burst. So the SVOM sample is selected considering the entire sample of short gamma-ray bursts observed by Swift, and we added also the ones that were defined as gamma-ray bursts with extended emission in the GCNs. Then we selected the ones with low galactic extinctions and with a prompt Swift XRT observation, less than 120 seconds. And then we selected the one with a peak photon flux in the BAT band higher than 3.5 photons per centimeter square per second, which is the 4 times energy threshold of the BAT instrument. So we obtained a sample with 53 short gamma-ray bursts, 11 on which with extended emission, and a redshift completeness of 79%. The BAT6 sample has the same criteria, but it has a peak photon flux set at 6 times the energy threshold of BAT. So first, we identified the initial pulse and then the extended emission using the BAT light curves, and we noticed that there are 2 classes of short gamma-ray bursts with extended emission. The one that we called pulse-like and the one that we called tail-like. The main difference, as you can see, is that the extended emission is very faint in the tail-like gamma-ray bursts with extended emission, which makes very difficult the determination of the peculiar energies of the extended emission as the energy peak. Then we studied both the prompt emission and the afterglow emission, studying this for the prompt emission, the spectral analysis, computing also the hardness ratio and the EP-K ISO relation. And we performed also a temporal analysis studying the spectral lag. Then for the afterglow emission, we studied the XRT light curves and we performed a morphological classification. And then we studied the optical light curves and the environment. So for the spectral analysis, we computed also the hardness ratio in the band from 50 to 100 keV and from 25 to 50 keV. And the idea was to identify if the initial pulse behaves as a short gamma-ray burst and the extended emission as a long gamma-ray burst. And here are the results. So as you can see in the left panel, we plotted the spectral photon indices and in the lowest, the hardness ratio duration plot. And we have that there is a transition R to soft if we consider the initial pulse and then the corresponding extended emission. But there is no clear dividing line because some extended emission as hard as the initial pulse of another event. Then we compare them with the long gamma-ray burst of the BAT6 sample in yellow and the short gamma-ray burst of the SVOM sample in red. And as you can see, we performed also a KS test, and we obtained that in hardness, the initial pulse is similar to the short gamma ray burst, but we cannot say the same for the extended emission and the long gamma ray burst. And we also performed a KS test for the duration of the initial pulse and the extended emission, and we obtained that the initial pulse and the extended emission are statistically longer than the short and long gamma ray burst. Then we studied the EPK-ISO relation using, where available, Fermi and Conus data, and we obtained that for the initial pulses, they lie in the same region identified by the SBOT4 sample, so a short gamma ray burst, but we constrained the energy peak for only one extended emission, which lies in the overlapping region between the short and long gamma ray burst of the BAS6 sample in gray. Then we studied the spectral lag, which is the difference in arrival time of high energy pulses compared to low energy pulses, and we obtain for all the phases null spectral lag. But we cannot consider the spectral lag as a key parameter to distinguish between short and long gamma ray burst. Then for the X-ray afterglow, we studied the XRT light course, and as you can see, short gamma ray bursts with extended emission are brighter than short gamma ray bursts at early times, less than 400 seconds in observer frame, but this difference completely vanishes if we consider late time in observer frame and the whole emission in rest frame, where short gamma ray bursts with and without extended emission are less luminous than the long gamma ray burst ones. Then we performed a morphological classification using some models presented by Margutti in 2013, which are simple power law decay or smoothed broken power law with one or more temporal breaks. And we obtained that short gamma ray bursts with extended emission show more complex light curves than the short gamma ray burst standard. And then we studied the optical afterglow and the host galaxies properties, and we found no differences between short gamma ray bursts with and without extended emission. So, in the end, short gamma ray bursts with extended emission are similar to what? If we consider the initial pulse, we notice that it is as hard in spectra, in prompt spectra as the short gamma ray burst, and it lies in the same space parameters identified by the short gamma ray burst in the Amati relation. For the extended emission, we found no similarities with long gamma ray burst for the duration and the hardness of the prompt emission, and also for the Amati relation, because we constrained the extended emission for only one, the energy peak of the extended emission for only one event. The main difference is the complexity of the XRT light course, so the X-ray afterglow. So we can say that the short gamma ray bursts with extended emission have more complex light course than the short standard. So that's all. If you have any questions, I'm glad to answer them. Okay.
Thank you very much. I wanted to ask, do you think there are different progenitors for these two short GRBs with the extended emission and without?
Yeah, we performed only a phenomenological study, so we didn't investigate the progenitor, the difference in the progenitors. But we noticed that there are some similarities with the short gamma ray burst, so these can maybe indicate that they share the same progenitors, but we didn't investigate that.
Yeah, just a note, when I was looking at the magnetar flares, they also showed a subfraction, let's say a flare with an extended emission, let's call it, but not a flare, burst with an extended emission.
Okay.
So which was quite interesting to see the similarity. So maybe a similar process.
Thank you for the very nice talk. I just wanted you to ask you to go back to the second to last slide, because you briefly mentioned something about the host galaxies, which I did not really get.
This one? Okay.
Yes.
Yeah, we investigate some properties of the host galaxies for the short gamma ray burst, and we found basically no differences. As you can see, in blue, there are the short gamma ray bursts with extended emission, and in red, the short gamma ray burst of the spot for sample. So we found no differences between both of the population.
Okay, I see. Thanks. Do you believe it is so? As I understood, you divided this burst into bursts with and without extended emission based on the classification in the GCNs, or claims in the GCNs. Do you think how difficult it is to come up with a definite classification criterion to distinguish the two classes?
Yeah, we need a clear definition of the extended emission, which is missing right now. I don't know, in this study, we found no clear parameters for which we can say, okay, this is a short gamma ray burst with extended emission, and this is not. Also, if you see the maybe the results for the spectral analysis, there is no a strict divide between the short gamma ray bursts with and without extended emission, so it's very difficult to define them.
So it is possible that these are actually the same class, right?
Is it possible?
Thank you very much. It's very interesting. I think that at the beginning you mentioned that you had two different subclasses regarding the temporal properties of the extended emission. Yes.
Okay.
And I wonder whether you tried to compare the properties of these two subclasses, especially the first one would be interesting to compare with long GRB properties.
Okay, yeah, the main difference in this study between this population is that we struggle to find the energy peak for the extended emission for the tail-like events. So there are no differences between the whole study. The only difference is that, yeah, it was very difficult to compute the energy peak because we have a low signal.
Thank you.
Yeah, how about the event rate of those GRBs with extended emissions?
What, sorry?
Event rate, volumetric event rate.
So in this but for sample, we have 11 GRBs with extended emission in like 53 events, short gamma ray burst. So it is like 1 to 5, 20%. Yeah. Okay.
Sorry, I want the first slide. It's not the first. How to move it? Okay, thank you. Okay. So that's my introductory slide. I need to also mention my collaborators and institutions, so that's why it is important. Hello everyone. My name is Agnieszka Janiuk. I'm professor at the Center for Theoretical Physics, Polish Academy of Science. And in this talk, I will try to convince you that the accretion disk winds are important ingredient to understand the kilonovae and their complete multi-band, multi-component, multi-messenger picture. So kilonova appear when the binary neutron star mergers eject material rich in heavy radioactive isotopes. The BNS mergers are the safest channel of the information, and it was suggested already theoretically in 1998 by Lee and Paczynski that such event should be observable. For detection, people had to wait a little bit. The first confirmed kilonova 2013, but we heard already today in the morning that some other candidates for the past kilonova can be searched for in the catalogs. And dynamical ejecta from these compact binary mergers are sufficiently massive and energetic to explain the emissions of the order of 10 to 40, 10 to 48 x per second in a time scale of a week. However, the subsequent accretion disk and subsequent accretion process in general can provide blue air emission, if only if it is not absorbed by the former ejecta. The kilonovae are having already nice data. Here, these light curves in various bands were obtained for the GW17017 source. And they have shown that there are blue and red components likely originating from two different media, two different components of the system. One of them being lanthanide rich, the other lanthanide poor. The lanthanides are those elements whose atomic structure allows for a number of bound-bound transitions, and that's why they are able to absorb and re-emit the photons of certain frequencies into redder bands. And these lanthanides are one of the features that appear in the R-process nucleosynthesis. R-process nucleosynthesis is the rapid neutron capture. So if we have fast streams of neutrons being catched by the nuclei on a very short time scale that is much faster than the beta decay of those nuclei, then we can form heavier and heavier elements, and we can see characteristic pattern of the R-process nucleosynthesis and its three main peaks together with these lanthanides and also actinides. And the pattern and formation of the heaviest elements depends very much on the neutronization of the medium, which is quantified with the value of so-called electron fraction, defined here as the ratio of the number densities between protons and baryons. So if it is low value, then it means that we have highly neutronized matter. And the compact binary mergers are a natural site of these very neutronized ejecta. People are simulating them with either hydrodynamics, multi-particle hydrodynamic codes, or numerical relativity codes. You can see here two examples, but of course there is a number of beautiful works published in recent years. The right panel shows outcome of the simulation of the binary neutron star merger, while the left panel shows the outcome of the simulation of the black hole and neutron star merger. That channel is also important. However, we need to take into account the parameters of the binary system. This compact binary system may be not always producing electromagnetic emission if the neutron star is just swallowed by the black hole and leaves no remnant matter. But here, as you can see, the simulation resulted in the formation of this remnant material, very neutron rich. I'm not doing that kind of simulations because for all my scientific life, I've been involved in black hole accretion modeling in various contexts, so active galaxies, X-ray binaries, accretion disks, and finally central engines of gamma ray bursts, which are also nicely explained by the hyperaccretion of matter towards a newly formed black hole. So here we have the black hole accretion disk post-merger system, while the black hole either was there already or it has been formed after the hypermassive neutron star after the coalescence has collapsed eventually. And we can model this process by solving a set of magnetohydrodynamic equations in general relativity. And for the problem of interest here, we need to support our equations with the proper equation of state, which is no longer an ideal gas, as it was used for the code before to study the AGN disks. Now we are in the GRB disks and post-merger disks. So our code now, the version which is publicly available is the older one, but still may be useful for pedagogical reason. One can take it and play. We compute the Fermi gas equation of state numerically by solving these Fermi-Dirac integrals and tabulate them during the simulation. And finally, we post-process the results by nuclear reaction networks, which was mentioned already. Several different networks are available. The one we use is Skynet. So here are some results. We obtain these quints. These quints are real. They can be probed by tracer particles. In our simulation, we can estimate the mass loss via these outflows by integrating the particle content to obtain the numbers between 2 and 17% of the initial disk mass. However, this is just a lower limit because one can use a more detailed criteria like the geodesic criterion or Bernoulli criterion to estimate the unbound mass in the system. The details are sensitive to the engine parameters, and in particular, the black hole spin and magnetization of the disk are important for the distribution of velocities in these tracers and also for the distribution of the electron fraction. So the more magnetized disks in general produce faster outflows. They reach up to 5% of the speed of light. And faster spinning black holes produce actually more broader distribution of electron fractions in the wind, which is important for nucleosynthesis. And it is important for the ultimate light curves that could be somehow related to the observations. Here, these synthetic light curves are obtained from simple prescription, that is some semi-analytical fit proposed in the literature some years before. I have to notice that these fits assume a fixed opacity, which is no longer true. Of course, it was never true, but the numbers here are kind of rough estimates and must be revised. However, important and probably not changing qualitative feature that we will argue for is the correlation between the black hole's spin and the ejected mass. And in the context of the models, we use several different scenarios to either mimic the binary neutron star or black hole and neutron star merger system, and they should result in different light curve profiles. What is important for the kilonovae that are associated with gamma ray bursts and the jets, at least one such source is known already, and I hope for detection of more of the kind, is the jet interaction with the accretion disk winds. The accretion disk winds are very important to shape the jet, the cocoon structure, and its energetic distribution, radiative properties, kinetic and thermal energy profiles as seen here. And we obtain more narrowly collimated jets for the binary neutron star scenario rather than for the black hole and neutron star. Here are some plots of the YE stratification, electron fraction stratification in these winds, also hints for some dependence on the progenitor type. Currently, we are using updated version of my code, which is based on the 3-parameter proper equation of state, and the neutrino leakage scheme has been implemented. We still study the magnetized winds and weak jets that are launched, and chemical evolution of these winds followed by tracers is visualized here in the bottom of this slide. The two plots show the histograms of the YE versus velocity distributions at the early time and at the late time of the disk evolution. So you see how the electron fraction is distributed. At early times, we have slower tracers with more broader electron fraction profiles, while at the late time, we have fast tracers reaching the outer boundary with the electron fraction above 0.4 already. We study the nucleosynthetic outputs across the different engine configurations. The output varies, and lanthanide mass fraction spans nearly 2 orders of magnitude. Here, the last column of this table shows some numbers that is like between 10 to minus 3 and 10 to minus 2 in the lanthanides. We also have some numbers in the paper about the europium to iron mass ratios and heavy to light ratio dependence on the central engine properties. So if you want to see more details, I just refer you to the work that was published actually last month. And now the work in progress, I want to advertise because my student Joseph Sadji is involved in that, and he just put a proposal for supercomputer time. So I like to say that it is important. A new calculation that we are planning to do is the radiation transport calculations. Over our results, radiative transfer will be done by means of the super new code, multidimensional Monte Carlo code available together with the line bin opacities from the NIST database from Los Alamos and suite of relativistic atomic physics codes, detailed lanthanide and actinide opacities, as well as the iron group light process elements are used here. And this is the last information about yet another channel that is invoked from time to time in the kilonova community. Collapse are a bit controversial because even though they can also have neutron-rich disk outflows and have been proposed as a major R-process sites, these disks may be important for cosmic heavy element production, as some people suggest, but their optical and infrared emission may be masked by the supernova light, so it's questionable whether we can detect them or not. Still, the long GRB associated events reopened the debate about the collapsar-driven engines, and the paper I just found yesterday on arXiv proposes such scenario. This is the cartoon plot, and in below it's our numerical simulation plot. Is the accretion disk structure volume rendering map from the numerical simulation done by another student of mine, Piotr Płonka, who nicely rewrote my old code to GPU accelerated version, and that's how it's possible to finally use this code to the results. So this is the conclusion slide. These quints are important feature, important component which regulate the transients. These quints are bridged between the kilonovae and GRBs because they, on one hand, they can regulate the lanthanide opacity through the stratification of the electron fraction and provide baryonic medium that shapes the relativistic jets. Their properties are tightened with engine parameters and nature of the progenitor, binary neutron star, black hole neutron star, or maybe collapsar, and it is central for their multi-messenger interpretation. One more summary, and thank you to the supercomputing facilities.
Nice talk. If I understood correctly, you're doing simulations in a static space-time where the spin is fixed, right? So how much?
Always here in the collapsar model, we have the dynamic space-time because the mass and angular momentum of the black hole change as well as the Kerr-metric. But in the former ones, here we have a static space-time because the black hole mass and spin are fixed.
Yes. Okay, so my question is regarding that. Most of the community is doing with static space-time with fixed spins. Don't use dynamical space. How much of an impact does that make if you don't have dynamical space-time and you just, in terms of the disk outflow?
I mean, in terms of the post-merger accretion disk, doesn't matter too much dynamical space-time if the mass of the disk is and accretion rate is slow. Yeah, So the mass of the black hole will not increase too much over a short time, and the spin will not change. So we tested this. It's negligible effect in the post-merger black hole accretion disk, but not in the collapsar case. In the collapsar case, you have huge amount of mass and angular momentum going through the horizon of the black hole, and the metric will change. So that's what we are doing in the last code. Yeah.
First of people start to prepare. Maybe I'll step one more. They just already.
Hi, thank you for the really interesting talk. I know nothing about this, so I have a very basic question, I think.
I need to change my glasses then.
With the collapsar disk winds scenario, what are the chances that the our process material and the material that's formed in the disk winds actually escape the system if you still have all this mush and collapsing star going on around it?
Yes, so it's a great question, and I think it is very difficult. First of all, for the collapsar jet is kind of difficult to break out through this supernova, pre-supernova material. It has to be a stripped envelope star, first of all, and then for the accretion disk winds to be emerging through this medium is again very difficult. So I think it's one of the channels theoretically proposed, but to be studied in more detail, and I think the results will show.
Okay, thank you.
Yes. They should be in the order that was in the. Sorry about that.
All right, so hi everyone. My name is Filip. I'm a postdoc at KTH in Stockholm. And so this is work that we did together with our groups, and it's for gamma ray burst prompt emission, and this is for subphotospheric shocks. So basically what we did is that we have a 1D special relativistic hydro simulation, which we've added Monte Carlo radiation transfer to. And so that means that the radiation is affecting the hydro, so they evolve in parallel. And the only thing that we start with is a profile for the Lorentz factor going from 40 to 400 smoothly. So that means that when you press play, this is going to launch a collision, and it self-consistently launches a forward and a reverse radiation-mediated shock because it's below the photosphere. And so that's what you see in these 6 panels, the evolution of these 2 shocks as a function of time. And then these photons go out and the optical depth drops, and then they will just decouple self-consistently. And that forms the observed signal as you have the light curve in the top right and then the spectrum in the bottom right. And the spectrum is very GRB-like. It has a low energy slope of -1 and a high energy slope of -2.5. And then you have a spectral hardening at low energies, which is also seen in gamma ray burst. So if you want to talk more about this, I think it's a very beautiful work, then please come and talk to me. Thank you.
Hi all, I'm Soumya Gupta from India. I'm doing a PhD there. So the motivation of this works lies in the problem that multiple models give a statistically significant fit to the prompt emission of gamma ray burst. So the idea come to us like, what can we do, which is a model independent quantity. So whatever the model fits best is not a problem to us. So what we defined is a spectral width of the GRBs in nu f nu log energy space. So what we find is particularly that if you compare it with the theoretically single emission thermal and non-thermal models, is that it should be tend to narrow down with the time. But what we observe for these particular two bright GRBs, 220426A and 230812B, is that both tends to get broader with time. So both are contradicting what we tend to possess from the generally interpretation from the low energy spectral index of the band or the cutoff power law function. So the possible explanation, it could be that there are multiple emission zones that are going with the time. And this can be visualized under the turbulent magnetically reconnectingly growing plasmas, which is also a model given by Benzang. This is ICMAT model. So I can give a short answer to the title is no. So if you are interested in the details of no, you can contact me, or there is a QR code in the poster outside for the recently published work. Thank you.
Hi everyone, my name is Megha. I'm a first year PhD student at the University of Ferrara. So very briefly, I'll talk about what I do. So I work on modeling radiative transport in double white dwarf mergers. So first of all, can double white dwarf mergers survive without explosion? The answer is yes, they do. And they may produce faint, rapidly evolving optical transients, but none of them have been confirmed yet, so far. So the challenge that we have right now is with semi-analytic models, we cannot fully capture the effects of radiative transport on energy deposition, thermalization. So what I basically do is I use POSIS, which is a time-dependent 3D Monte Carlo radiative transfer code, to model these kind of systems, these kind of ejecta. So if you can see the first image, which is a energy deposition profile. So this is basically how the energy from a remnant magnetar spinning down propagates through the ejecta and later emerges as an observable luminosity. And if you see the second one, which is a light curve evolution, so you can see when we compared our work with a semi-analytic model, we do found that radiative transfer does change the expected observable luminosity. So why do we care about this right now? So as we all know that Rubin LSST is beginning to probe all the unexplored transient space, these kind of models can be really helpful. They can act as templates to identify more of these kind of DWD merger transients. Right now we are in the phase of looking into the broadband light curves and spectra to know more about the characteristic features. So yeah, if you are interested, then there's a poster and also I'll be here. So yeah, thank you.
Okay, so hi everyone, my name is Manuele and I'm a PhD student from the University of Ferrara, Italy. And today I will very briefly talk about our last work, which has been accepted like 2 hours ago, so perfect time. And please, if you have any question, come talk to me during the coffee break. So the goal of this work was to get insights on the origin of gamma ray burst prompt emission, which is still an open point after all this time. Specifically, what we did was providing the first quantitative calibration against real data of the so-called internal shock model, which is one of the most discussed theoretical frameworks to explain gamma ray burst prompt emission. So the model was optimized within a machine learning framework by using a genetic algorithm, and it can reproduce several temporal properties observed in real light curves. And there on the right, you can see a few examples of synthetic light curves that, let's say, as they would have been seen by SwiftPath in the 15150 keV band. And eventually, this technique, this kind of analysis allows us to get insights also on central engine activity. Specifically, what we found is that the number of shell ejected per GRB they are well described by the so-called generalized Ziff distribution, which is the same distribution that rules the magnitude, frequency, behavior of earthquake, which means the more intense the earthquake and the less frequent they're going to be. And second, we found that the rest frame shell ejection times follow a negative exponential distribution, which means, let's say, just like radioactive decay, and this points towards a constant and independent probability per unit time of being ejected. So please, again, if you have any question, come talk to me during the coffee break. Thank you.
So I'm Resmi from the Indian Institute of Space Science and Technology, and this is a work done in my group with my younger collaborators. We are trying to understand how off-axis, how to identify how off-axis burst using both prompt emission and afterglow. So we have off to the prompt emission phase, we have used a simple model of geometrically and optically thin shell moving with a bulk Lorentz factor gamma with an opening angle of fixed opening angle of 5 degrees. It's a top hat jet, and we try to assign different viewing angles, isotropically distributed viewing angles, and try to get them detected using GBM threshold. And obviously, due to relativistic beaming, the higher viewing angle GRBs do not get detected. Due to the relativistic effects, there will be definitely a change. There has to be a change in duration and this hardness. So we try to simulate the duration hardness plane, and this is a very kind of pilot study, so this doesn't really follow any sort of distribution. We randomly distributed different pulse width and Lorentz factor and viewing angle, and we obtained this sort of, what we really found was the low duration ones due to the lack of the off-axis ones with the lower fluence, because the fluence get reduced due to beaming effects and don't get detected. So, but we do see a population of soft burst, which are close to the jet angle. Another thing we tried to do was to place identical GRBs at different viewing angles and place them at closer. As we place them closer and closer, the duration gets changed. Sorry for this. Is the reciprocal of this. Back off to afterglow, we used early rising optical afterglows with both X-ray and radio are not suitable for this purpose, and we try to see if we can identify any signature from here. What we find is that these are all Gaussian off-axis bursts with this broad peak, and yeah, that is we are trying to combine both and try to secure the identity.
Okay, I'll try to be concise to lose more time. Okay, thank you. Okay, so this special talk and this poster are about revisiting the internal shock model. So we know that the internal shock model has issues, especially regarding the efficiency of the process, because we need to have fast cooling synchrotron if you want to have the efficiency that is observed from afterglow. However, we don't have the spectral slopes that goes with the fast cooling of the synchrotron. In our model, we've seen that by redoing the full hydrodynamics, we have actually two shock fronts, so two zones that that contributes to the flux, which solves a bit this issue. And by doing some modeling with an array of numerical simulations, we extracted and created a surrogate model that we are now using to analyze properly GRB single pulse data. So I'm showing preliminary results now where we just found one parameter, the timescales, and why it's important to use the fully spherical rather than pure simple analytics. But this model is being developed a bit, and now we're trying to apply it to get all the relevant physics, the relevant flux normalization, time normalization, and energy normalization, as well as jet parameters that goes with it, just from looking at the peak energy and the peak flux from single pulse GRBs. Thank you.